So there's this one weird thing that's killing furnaces and air conditioners everywhere. I'm Nate Adams, CEO of HVAC 2.0, and often known as Nate the House Whisperer. So what we're going to talk about, this is a very real thing. This is not fear, uncertainty, and doubt. About half of systems are at serious risk of early failure, and I'm going to show you the numbers on that later. But first, let's talk about what happened. So back on July 3rd of 2019, which is just a little over 2 years before I'm recording this, the Department of Energy changed the type of furnace fan that goes into new furnaces. They went from an old school kind that was not very sensitive to a new school kind that is. And that has been already causing more problems than perhaps I would have expected. And what is that weird thing? The weird thing is called duct pressure. It's pressure inside the ducts. And the easiest way to think of this is think of a balloon that is blown up and that is either tied or that you're holding the end of. There is pressure inside that can't go anywhere. The technical word is static pressure because it's pressure that's static. It can't go anywhere. Now, if a system is installed well, this isn't a problem. The trouble is most aren't. So like I said, only 2 years later, we're hearing a surprising number of failures. So duct pressure, easiest way to think of this, besides being in a balloon, is this is the blood pressure of your HVAC system. And we're going to take that analogy a little bit further shortly. For my technical friends that are watching this, this is also known as external static pressure because technically it is external to the system or the box itself, so it's before and after the furnace of the heat pump. And then it's often shortened to static pressure. But we're just going to call it duct pressure because it's easier just to kind of understand. And if you're a homeowner, and that's my intention here, it's easier just to think of it that way. Now, this is a well-known problem, by the way. So there's even a meme for it. High static, like I was saying, that's the technical term for it. Here's Pac-Man eating ECMs, which is the type of motor that is the problem here. It's both a good and a bad thing, as we'll get to. But this is a well-known thing in the industry. Now, the other side of static pressure is velocity pressure. So if you open up the end of that balloon, you're going to get velocity pressure coming out the end of it. Duct works the same way. You need enough pressure inside the ducts so that air will come out. So you have to have duct pressure if you're going to have velocity pressure. So if to duct pressure, then velocity pressure. It's a requirement. And just like a balloon, if it's too high, the balloon pops. If it's too low, there's no flow coming out of the end. So let's move this over to thinking about your heart and circulatory system versus your air handler or the furnace fan and the duct system. So there is a place that you want to be when it comes to blood pressure. So you want to be between 90/60 and 120/80. That's just right. If your numbers come in there, your doctor is not going to be pushing you to do something different in your life. Now, if you're on the very high side here, above 160/100, you're at pretty high likelihood of a heart attack. So that's one of the reasons that this is so commonly measured. I mean, you go to the doctor, they're going to check your height, your weight, and your blood pressure. Those are the key things they're going to check because they help give you an idea of what's going on very quickly. So duct pressure is just the same way. So where blood pressure, you've got a sweet spot between 90/60 and 120/80. In duct pressure, you want to be between 0.08 inches of water column. Don't ask me why this is the metric. It's the metric. Blame the British. They're the ones that gave us these crazy systems and then abandoned us to the metric systems. So they can call us traitors, but when it comes to metrics, I call them traitors to the metric system. But you want to be between 0.08 and 0.3 inches of water column. If you have a system in here, it's going to be quiet and it's going to use very little energy compared to the previous system. If you're too low, you have a problem. Like up here, if you're too low, either you're dead or you're bleeding out and you're going to be dead. So that's a bad thing. And in duct pressure, you can be too low as well. Although frankly, the only time I've seen this is after we have done a project and I've freaked myself out on how low the pressure was. And in those cases, the system still worked fine. So I don't think this is a major issue, and it's certainly not common. Just like blood pressure, your main issues are on the high side, not the low. Okay, so let's take a look at what this looks like. like I said, between 0.08 and 0.3 is good. Where you don't want to be is upwards of an inch of static pressure. So most furnace fans and air handler fans, if you have a heat pump, are rated for a half an inch of static pressure. You can go look through the catalog or the manual, and it's probably going to say half an inch is what they're rated for. When you get to double that, with the new kind of motors, these tend to die, and they can die pretty quickly. Now, if you are just above the 0.7 range, 0.7 is generally considered to be where the risk factor of early failure starts to go up. But if you are at 0.7 or above, your fan is going to be noisy, more than likely, or expensive to operate. So I did a comfort consult for one fellow. We turned his fan on, and his duct system actually oil canned. It went boom, boom, when it blew up with air. And I'm like, oh man, that's not good. I got to go get my drill, and checked with the static pressure, and he was over an inch. So when that's the case, they can be very expensive to operate and prone to early failure. And as I'll show in a data set here shortly, most systems are at some risk of problems. Anything over a half an inch is at risk. Is it a huge risk between 0.5 and 0.7? Nah, probably not. But it might be, depending on whether the fan's sensitive or not. And here are what the main risks are of this. So the big one that we're talking about here is a failed fan motor. It's where the fan motor burns up because it's working too hard and can't do its job. A really serious one is a cracked heat exchanger, because you aren't moving enough air across the furnace heat exchanger, so it gets too hot, and then metal will crack as it expands and contracts too much. So that can be a problem, and when it cracks, that can lead to carbon monoxide poisoning. And this is a non-trivial risk. My mom actually almost died of this from cracked heat exchangers. Frozen air conditioner coils, if you've ever had the indoor unit of your air conditioner just totally freeze into a literal block of ice, that's probably because airflow was too low, because static was too high is usually what's going on. If you have zoning, this can lead to very noisy systems or early fan failure. And you can also get broken compressors. Because basically how air conditioning works is it's switching the phase of the refrigerant from liquid to gas and back again. And if it doesn't have enough heat to remove, it can actually come back in as liquid, and it will then break the compressor, which is a very bad thing. Now, next up, let's talk about the two types of fan motors, because this is what fundamentally caused the issue here of the one weird thing. So PSC, don't ask me what it stands for. This is the old school technology. So I picture this like Jack Lambert of the Steelers. I mean, that was a dude you just didn't want to mess with. Tough, uses a ton of energy, and seldom breaks. So it's a nice technology from at least that one perspective. The new one is called an ECM. It's an electronically commutating motor. So it's an EC motor as opposed to an ECM motor, because I will get a hard time if I say ECM motor. But these are touchy. So I view these like a soccer player that's a bit of a prima donna. You touch the guy on the ear and he falls over writhing in pain. He's obviously having fun here, but this is very much what they're like. So here's how this ends up working. So when it comes to PSC motors, they just don't care when there's really high static pressure. In fact, what they end up doing is very similar to, I picture Scooby-Doo running, and his legs are flailing, but he's not actually going anywhere. That's what PSC motors end up doing. They spin, and they actually use less energy against higher static pressure, but they don't move any more air, where ECMs are trying to move more air. So if you put an ECM against high static pressure, anything over 0.7, they don't like it, because they will ramp up to move as much air as they have to, and if they ramp up beyond what they're capable of, they can burn up, and often they do. So I want to take a look at the energy use charts. This is a general chart. This is just to show the shape of the curves, so some of my technical friends are going to watch this and have a cow. Chill. So a PSC motor, its usage looks like this as airflow goes up. So they don't turn down super far, only to maybe half of what the full speed would be. So if it's a 1200 CFM fan max, it probably doesn't turn down below 600. And CFM is cubic feet per minute. And so the Scooby-Doo effect is what happens up here. They actually use less energy as the airflow needs, or really it's the pressure, get higher. And the reason that this regulation was put into place is an ECM, an electronically commutating motor, if you put it up against low duct pressure, it uses almost no energy at low speed. Like I'm clocking these between 15 and 40 watts. And I mean, it's a few LED light bulbs to move 300 cubic feet per minute. So they use almost nothing at low speeds, which is, again, why right-size variable speed equipment is important, because most of the year, your HVAC is going to be running on low, and you're going to be taking advantage of this. And then when they are ramped up, they still use a lot less energy than the PSCs. So they use less power at all points with an ECM versus a PSC with a low duct pressure situation. Now let's flip that script and let's put that ECM against high duct pressure. So the energy use curve, according to Jim Bergman of MeasureQuick, not only is it a cube function, but it's actually a to the fourth function. So when you start working it hard, energy use goes up really quickly. It's a very geometric looking curve. And so this is where the trouble happens. So you actually use more power with an ECM than you do with a PSC. That's a problem, because the other thing is when you're getting to those levels, you're running that inch of static, or you're running high, and this is where your likely fan death happens in 1 to 3 years. So this is something to be aware of. Now let's take a look at what the government had in mind as they did this. So this is out of the ACHR News, Air Conditioning, Heating, and Refrigeration News chart that I pulled from one of their articles. And this is what the Department of Energy was planning on as far as static pressure or duct pressure. So units with an internal evaporator coil at a 1/2 inch. That's a heat pump. So that just has the coil. It's the fan and the coil. That's what heat pumps have. Units designed to be paired with an evaporator coil. So this is a furnace, and the evaporator coil is an air conditioner. So it's a furnace plus an air conditioner, 0.65 maximum. And units designed to be installed in a mobile home at 0.3 of an inch. So 0.5, 0.65, 0.3. Note that all of these are below the 0.7 that I'm talking about. So here's what the DOE assumption looks like on the chart. Now let's look at some actual data. So this is data from almost 800 systems, and it's nationally representative. So this is a pretty good data set, and it's a very rare data set. I'm lucky to have this. But this is static pressure on the bottom, and this is how many systems that there are in that category on the other axis. First thing to note, 1/2 inch is the rated pressure of just about every furnace or heat pump fan out there. If you look at it, they're rated at 1/2 inch of water column. Well over half the systems here are above that. Now, really important point, these are systems where there's a contractor that's actually measuring this stuff, and there's only a few % of contractors that are actually measuring, and some of these are likely post-install numbers, which are, if they're paying attention, probably lower than pre-install. So the odds are this data set is better than reality, not worse. And even with a better than likely reality data set, we still have over half of systems above 1/2 inch, which is where we don't want to be. Now, there we are. I'm just hammering that home. The real danger level, though, is agreed to be about 0.7 inches of static. So that is where you get into the danger zone, static pressure, duct pressure. This is where that meme comes back in. High static. Yeah, this whole area here, you're getting into risk. So if you are an inch and higher, this is where your failure in 1 to 3 years is likely from the fan. And if you are below that, in the 0.7 to 1 inch range, you still have pretty likely failure before the system reaches end of useful life. And because of the problems I was talking about earlier between cracked heat exchangers and frozen coils and things, this could still get you in trouble with the rest of the system, and this almost surely will. So it won't just break the fan, it'll probably break something else. And again, this is almost half of systems. It's about 47%. So here's where the issue is. I mentioned the Department of Energy assumption between 0.3 and 0.65 inches of duct pressure. Reality is half of systems, nearly so, are above 0.7. So almost half the systems on the market, and again, that's probably better than reality, are above that 0.65 maximum of the regulation. So this is what's causing problems. So let's talk about causes and solutions. So we'll go back to the heart and the circulatory comparison. So the main causes of this are that you have too much blood to flow because we're fat. So if you're fat, you have all that extra fat that has blood vessels in it, and it's more that your heart has to do all the time. So you're making it pump more volume because you're fat. And the other side is constricted blood vessels. And to be clear, I'm fat, so I'm guilty here too. But if you have too much blood to flow, because there's too much body to serve, or you have constricted blood vessels that are filled with garbage. These are the things that lead to high blood pressure and then a high risk of heart attack. Make sense? Let's translate that over to ducts. So the first one is there's too much air to flow, which means your equipment is oversized. So ballpark is every ton of air conditioning requires 400 cubic feet per minute. So a 3-ton system needs 1,200 cubic feet per minute. A 4-ton needs 1,600. As ballpark, it can be less. There's a whole bunch of factors in there, but rough numbers. If you can drop down a size, you're going to substantially reduce how much pressure is in the system. So I mentioned how energy use is a to the fourth power equation. Static pressure against increased flow is a squared function. So one example, a system I tested a few years back, I increased the flow of it 38%, which almost doubled. It was an 85% increase in duct pressure. That's how that works. So it's a pretty big deal. So you hit a wall with duct pressure, and you don't want to try and make that system use too much. So if you can downsize the system so it needs less, that is a good thing. And what that ends up doing then is right-sizing the ductwork. And so here's the simplest solution. You add what's called a bad, I'll show you what that is in a minute, and you downsize the system, which naturally right-sizes the ducts. So pretty consistently, here's what we see. We start with systems in the 0.7 to an inch range, maybe over an inch, and post-install, pretty much every system that we have done has come in between 0.08 and 0.4. And remember, 0.5, that's not like a hard limit, but that's where things start getting a little shady. But we have stayed below that with all the systems that we have replaced. Now let's look at what we call a SAD. Yes, it's a joke. You can laugh. That it stands for small air drop. So let's look at what that is. Here's a standard furnace. This is in a basement. This is super common in my part of the country. It's not common in a lot of places, but most homes in cold climates have basements. And here's what it looks like. So this is the return drop. So this is the air coming down, and then it turns and it goes up through the furnace. So this is the furnace flue, and this is the supply duct. There is a little tiny filter that's jammed in here that's trying to handle all this airflow. But notice how small this return drop, as it's called, because it drops to the furnace. Note how small that is compared to the supply. So this is 8 inches wide, and this is more like 24. That's not a good match, and that's very typical. An 8 by 24 is probably the most common drop size. Now, think about the airflow. So it's coming down here, turning, and coming up. If this was water, because basically at the pressures that we are running in our houses, air flows very similar to water. So if you picture water flowing through your system, that's probably not that far off of how it's actually working. So the airflow is coming down, and then it's asked to make it, well, first it slams into the ground here, and then is forced to turn around. that means that the air here is turbulent. Turbulence is bad when it comes to energy use. It's also not great for filtration, so who knows exactly what part of this filter is going to get hit, but the odds are, well, it's probably actually this part right here is getting hit with dirt to filter out, because the air isn't even hardly making it to the other side because it's in such a hurry to make that corner. So what that looks like is turbulent flow inside. So picture a mountain stream with a bunch of rocks in it. That's turbulent flow. Smooth flow is when you can't see any rocks or anything. It's just rolling along. Now, here's how this ends up working. So I didn't test in this particular system. That was before I was doing this. But let's say it's an inch of static because it was kind of noisy. So this is an actual picture that one of the HVAC 2.0 contractors sent me. And it looks like he has upwards of 6% of their systems that have the absolute top end system installed. 6% of them are above 1.1, which sends an error from the manufacturer that you need to either reduce the quality of the filter so it allows more airflow or increase the duct size. So the manufacturers know that there's a serious risk of failure and they have it programmed in at 1.1. And that was 6% of systems, so it's not non-zero, that's for sure. But say the system was at an inch before. I suspect it was probably closer to 0.7. But if it was in an inch, that means that that fan is at pretty strong risk of failure within 3 years. Now, the fix for this is called the BAD, or the big airdrop. And note, so this is the same system that was replaced later. I'm step back another step or two, but it's the same system. Note how big the return drop is. This is now 24 by 24. At install, this is not a big deal. It's marginally more labor and marginally more materials, but it's the same basic task that's being done, so it's not that big of a deal. And note that there is a filter horizontally right here in the system. So the air comes down, and as it comes down, now it's smooth, it's laminar, and it's hitting the whole face of that filter. So now it works really well. So if you dust a lot in your house, the odds are a good filter like this will knock down how much you have to dust. If you are concerned about COVID or getting sick, like basically anything that we humans get sick with, the pathogens travel in our small spit particles. And by running this through very slowly, you're going to catch most of those spit particles. So if you go look at the indoor air quality researchers, what they're recommending, they're pretty much all suggesting a MERV 13 or higher filter and then running a whole heck of a lot of air through it. So this lets you do that. Now, normally we would recommend that these ducts be curved going in here as they go down and come back up. And actually, it's the internal curve that matters more. But in testing this system, it wasn't a problem. There's so much space here that the air figured it out. It was happy air. And I mean, this is a quick illustration of what happy air looks like. So there's turbulent flow and laminar flow. So if you think about a wing, underneath the wing is laminar flow. It's not getting restricted. It's going right where it wants to. Going above is turbulence. So that's not what we want in this case. Now that same system, post-install, came down to 0.2 inches of static. And this frankly freaked me the heck out because I had heard that that was at a level where it was going to cause problems. And on low speed, it was at 0.04, which was really, really low and totally freaked me out. Turns out the system works fine. Now, this is a ranch. You may or may not get away with this in a 2-story, but you definitely can get away with it in a ranch. So take a look how nice and low that is. That's really green. And some people will say this is impossible. Well, we've done it a few times. It happens. Now, the BAD, by the way, is part of what we call badass HVAC. So there are 6 different functions that every HVAC system should be able to do. Every car can do 5. Most houses can't do any. I will link the video where I go into this in detail, but this is the basic idea of a BAD. So the air comes down through here, and you just saw the picture. Great big return duct. There's the filter. It turns and comes into here, goes up through the unit again. This tackles load matching, which is super important for comfort, filtration, which we've been talking about, dehumidification. This is a heat pump with reheat capability. We bring in fresh air, which is another piece on the health side. Mixing, which is done because it uses almost no energy if you've got big ductwork. Like I said, 15 to 40 watts on low, and most of our systems are less than 200 watts on high, which is maybe $20 a month if you run it 24/7. So it's not that much. And then humidification, depending on your climate. So that matters where I live. It might not matter where you do. So that's the bad. The other piece is downsizing, and I'm just going to touch on this briefly, but the easiest way to do this, the best way to do this is through what we call in HVAC 2.0, the comfort consult. So that's a blower door test that is a load calculation that is based on your blower door. It's based on your actual energy use, and you take the error bars from literally with the manual J, which is the industry standard calculation. It can be plus or minus 70%. It can be that wide. Is it always? No, but it can be, which is crazy. Plus or minus 70% is not a calculation. It's a guess. So if you want to narrow those error bars, you need to know energy use and blower door, and then it's best to understand what your thermostat settings are and some other things. That's all included in an HVAC 2.0 comfort consult. So if you are lucky enough to live near a 2.0 contractor, go get that done, because that will let you downsize, which will make your system quieter and happier. Now, to that point, most systems can be downsized between 20% and as much as 60%. The system that I showed you, that was a 120,000 BTU furnace that we turned into a 3-ton heat pump. That's 36,000 BTUs. So we went from 120 to under 40. So that was about a 70% drop in capacity for that system, and it heats the house. One of the easiest ways to understand, because almost all systems can be dropped to size, and many of them can be dropped to. So furnace sizes are typically about 20,000 BTUs, so 120 is the biggest, then 100, then 80, then 60. If you have a $100,000 BTU furnace, you can probably go to an 80 with very little risk, and you can probably even go to a 60. And the easiest way to figure this out is pay attention to your HVAC on a really hot or really cold day. Does it shut off? Then it's oversized. So in theory, it should never shut off when we hit design temperatures, which is the coldest 1% of the year, the hottest 1% of the year. The other thing you can do is get an Ecobee thermostat, because those will track the runtime of your system. So you can go look at a hot or a cold day and see what's going on. Or like I mentioned earlier, really the best option is to get an HVAC 2.0 comfort consult. Not meaning to sell, just having designed the whole thing and understanding all the intricacies of sizing HVAC well, you really need some more data, and that's going to cost a little something to do. But if you are worried about it, that's what goes in there. But the first thing is you want to determine, are you at risk before you start worrying about downsizing and any of this other stuff. So remember, the Department of Energy assumption was 0.3 to 0.65, and reality is that about half of systems are above that 0.7 that's risky, and definitely more than half are over the half an inch of static pressure that is problematic. So how do you figure out which way you have to go? Get tested. So if you have an HVAC 2.0 contractor near you, I highly recommend that you call them, and this is part of the free quote path. You can ask them to do a static pressure test for a nominal fee, and then you will understand, are you in trouble or are you in the safe zone? If you're in the safe zone, you probably don't have to worry about it too much. If you don't have any comfort issues or anything like that, you can just replace your equipment and move on with life. But if you are on the high side, because of that Department of Energy regulation, that could be a problem. So you want to understand what that is. So you want to understand your risk, and then they will be able to help you figure out what the path forward is to reduce that risk. So I hope this was helpful. That is the one weird thing that is killing furnaces and air conditioners everywhere. It's called duct pressure or static pressure. So I'm Nate Adams. Have a great day. If you enjoyed the video, you know the drill. Subscribe, click the bell, all that good stuff, and share and comment. Have a wonderful day. I'll see you next time. Bye-bye.